lab4report. So for lab 4, we're going to analyze the motion of a spring mass system where the ball is oscillating back and forth on a spring. And the main physics principles I use for this lab are Newton's second law, energy principle, and the conservation of energy. And the physics formulas are listed here. The kinetic energy equals to 1/2 times mv squared. The gravitational potential energy equals to the gravity force times the displacement. And the spring potential energy equals to 1/2 times ks times the square of L minus L0. And first I uploaded the video into Tracker, and I set the calibration length, the coordinate system, the same as the one in the lecture video. And since this video is different from the one in the lecture video, I set the frame range by myself. So it's here where the ball is just going to be released until the end. And there are two graphs generated by Tracker. So the first one is the y position versus time and the x position versus time. So because the ball is oscillating back and forth, there are two graphs. And these are the xy position data generated by Tracker, and I copy and paste this data to a CSV file in order to upload the data to GlowScript code later. And these are the data I used to edit the GlowScript code. So the mass of the ball equals to 0.402 kilograms, and the initial position, which I get from Tracker, so the x and y initial position, and the initial velocity because the ball is dropped from rest, so the velocity equals to 0.000 meter seconds. And then the period of oscillation, I chose the time range for 3 periods and divided by 3, so I got the average period of oscillation. And then the spring constant Ks, according to this equation, the K equals to 6.87, and the relaxed length of the spring, the L0. Since the ball is at equilibrium, so the weight force equals to the spring force when the ball is at rest, so I can calculate the L0 equals to 0.126 meters. And then I go to GlowScript. I change the mass of the ball, the position and velocity of the ball, and also the Ks spring constant and L0. And L equals to the ball's position minus the spring position, which is the origin. And L hat equals to L minus the magnitude of L, and S equals to the magnitude of L minus L0. And according to the physics formulas I listed on the previous slide, I changed the equations to calculate the kinetic energy, the gravitational potential energy, and spring potential energy, and the total energy equals to the sum of the three energies. And then when we only take the ball as the system, the gravitational force and the spring force acted on the ball are calculated here, and the net force equals to the gravity force plus the spring force. And I then apply the Newton's second law to update the ball's velocity and position, and also update the spring. And then I calculate the energy changes, so delta K, delta UG, delta US, and the total changing energy equals to the sum of the three energy changes. And then when I run the program, so I chose the CSV file. So this is the model, and there are two graphs generated by the code, the position versus time graph and the energy change graph. So when we first look at the second graph, the position versus time graph, we can see that the blue one is the model and the red one is the actual ball. So we can see this motion are pretty similar, and there isn't a huge difference. So this motion are pretty similar except for the model is oscillating vertically while the actual ball is oscillating back and forth. And when we look at the energy graph, we can see that the changing gravitational potential energy and changing spring potential energy oscillate with the same period. So it's the green one and the red one. And these changes are about the same size but opposite phase. And the delta K, the change in kinetic energy, are both positive and negative. So this is the blue one, and it oscillates twice as fast at the changing potential energy. And the orange line is the total energy change, so it's equal to 0. And for the what does it mean questions, so the first one is, for your model system, is the energy principle satisfied? It's yes, because according to the energy graph, the total energy change delta E, which is the sum of the 3 energy changes, is equal to 0, which corresponds to the energy principle. And the second one, using the data you obtained in tracker, make 2 separate estimates of the oscillation periods. So the first one, from the X position data, I chose this point. So it's 4.843 seconds and minus 0, and divided by 3 is 1.614 seconds, and the same as the Y position data. So we can see from these two results, these two numbers are pretty close to each other. So this is because the ball is oscillating back and forth. So the X position data, the oscillation periods from X position data and Y position data are pretty similar. And that's all for my lab 4 report. Thank you.